Right, then welcome to today's TransFlap seminar, which is a platform where researchers and engineers share and discuss recent advances in AI and machine learning, striking a balance between accessibility and mathematical depth. Today's speaker is Domingo-Enrich. He's a senior researcher at Microsoft Research in Cambridge, Massachusetts. He works on generative modeling, especially diffusion models and normalizing flows, deep learning for stochastic optimal control, high-dimensional hypothesis testing, and related topics at the intersection of machine learning, statistics, and optimization. Prior to this, he was a PhD student in computer science at NYU, advised by Juan Bruna, and a visiting researcher at Metafair Labs in New York City, working with Ricky T.Q. Chen and Brendan Amos. Thanks for being here and sharing your work, and the stage is yours, Carl.
Thank you. So I'll be talking about stochastic optimal control matching. I'll just get started. So first, I'll give you an overview of the content of the talk. I'll start with an introduction, where I'll talk about the stochastic optimal control problem. What is it about? Then I'll show some examples on robotics, sampling from normalized densities, and also important sampling for diffusions. There's a big example that I'll be leaving out, but that's just future work. And then I'll also cover existing approaches to solve this problem. And then I'll dive into stochastic optimal control matching, which is our approach. I'll first compare stochastic optimal control with normalizing flows, and that will be a build-up towards our algorithm. And then I'll present SOCM. I'll cover the main features of our algorithm, and then I'll present some experiments that support our findings. Finally, I'll have this other section, which will be basically like short derivation of the SOCM loss at the high level. Then the pathwise reparameterization trick, which is the technique that we used to find the loss. And then I'll talk about conclusions and future directions. So what's left to do in this field. Okay, so let's jump into the introduction. The theme of the talk broadly will be that good functional dependence plus low gradient variance gives rise to good empirical performance. And all of these terms will become clear, hopefully, by the end of the talk. So just to make this a bit more concrete, think of continuous normalizing flows, which were originally trained to maximize the likelihood of training samples using the adjoint method. So this is a long sentence, but what I'm referring to here is just, if you're familiar with the work Neural ODE, that's around 2018, that's what that work introduced. If you want to train a normalizing flow, you just need to maximize the likelihood of the training samples. And that involves basically backpropagating through the whole trajectory. If you look at diffusion models, these models are basically using a least squares loss to learn a score function or a denoiser, depending on the formulation that you use. So while continuous normalizing flows with maximum likelihood had this highly non-convex functional landscape, diffusion models now have a convex functional landscape. In particular, it's a least squares functional landscape. Just to draw the parallel with normalizing flows and diffusion models, currently stochastic optimal control is solved relying on the adjoint method, which is again a method that has this very highly non-convex functional landscape where you need to essentially backpropagate through the whole trajectory. And our work is about, basically completing the square. So we want to develop a least squares loss for stochastic optimal control. And that's what we set out to do. Okay, so now I'll present in a bit more detail what stochastic optimal control is. Control means that we want to control a system, like driving a car or managing investments, to achieve a desired outcome or behavior. And optimal means that, say, when we're driving from point A to point B, the optimal path would be the one that minimizes time and fuel. So we're actually minimizing something. And stochastic just means that the systems or processes are random and unpredictable. So we need to be robust to noise. So here I'm putting an example of a robot, but maybe that's not very appropriate because none of the examples that we consider in practice are actually physical systems. But I feel like this is easy to understand what the problem is about. So say you have the goal of moving the robot from an initial position to a final one in order to accomplish a task. The controls that you have would be like torque applied on joints or force applied by linear actuators. And optimality would be you want to accomplish the task using minimal energy while enforcing the constraints that you have on the joints. And here stochasticity would come from sensor noise, from unexpected user behavior, from variable conditions. So in other words, you want to have a system that actually works in real life. So you need to be able to handle this noise. Now, if you want to formalize all of this, the way it's done in stochastic optimal control is through stochastic differential equations. So we have this uncontrolled process, which satisfies, again, this SD. So you start from an initial distribution P0, and then you have like an SD that has a drift term and a stochastic term. So here X is just this process that goes from the interval 0 to T to the Euclidean space. In the case of the robot, that would be angles and angular velocities of each joint of the robot, for example. P, which is here, is the base drift. So in the case of the robot, that would encode Newtonian mechanics. Lambda is the noise variance, and sigma is the covariance matrix. You can actually merge these two. So here I just put them separate because that allows you to cover the case where you don't have noise. But yeah, if you want to think of them as a single thing, feel free to do that. And that would just be like how much stochasticity you have in your system. Of course, the bigger lambda and sigma, the more noise you have. And once we have all of these things defined, we can go to the control process. So this is a process where we have an additional term that's sigma times u. And yeah, u is just a control. So it's a vector field that takes in state variable and the time variable. So that's Euclidean space times this interval. And it outputs a vector. In the case of the robot example, that would be the torque or the force applied to each joint or each linear actuator that you have in your robot. Now, if we want to see this more graphically, we can think of an uncontrolled process, in this case, which would be in one dimension. So you can think of, in this case, a process where B is 0 and sigma, you can think of it as a constant in time. And you have something like this, right? So you'll have trajectories that just evolve randomly due to the noise introduced by the stochastic term. And then at some point, there are these barriers with two holes. The trajectories hit the barriers, but some of them are actually able to go through the holes, progressing further. When you have a controlled process, what that control allows you to do is basically it allows you to modify the behavior of your system. So in this case, the control was actually learned, basically such that most trajectories will go through one of the holes. And it really changes the picture, because before we didn't have any that would go through, or that would be very unlikely for this process up here. But when you add u, you essentially change the behavior and you allow trajectories to go through the upper hole. Now that you're a bit familiar with the framework, like the SD framework that we're going to use, I'll present the stochastic optimal control problem, which is of this form. So you have this optimization problem where the SD that we're using is the controlled SD. So this is fixed, and we want to learn the control U. And what we're trying to optimize is this objective. So again, XU is the control process. This term here is called the state cost. And if we're going back to the robot example, the state cost is basically something that we want to be small. We set it to be small for physically possible configurations, and we want to set it to be large for impossible ones, because essentially since this term is something that we're adding to the cost, we want to make this expectation of this term as small as possible. And if we set the state cost like this, we'll essentially be driving our system towards regions which have low state cost. G is the terminal cost. So we want to always set Z such that it's small for the desired final configurations and very large otherwise in the case of the robot. So again, F and Z are just used basically to drive our system. We'll set them such that our system ends up at regions where F and Z are small. And then one thing I didn't cover here was this first term. This is the term that basically measures how big the control is. So we don't want the control to be too large because essentially, well, I mean, otherwise our system changes completely. And also going back to the robot example, that would mean that you're actually using infinite force or infinite torque, which is not realistic. So this is kind of a way to balance out. You want low costs, but also you don't want huge controls. Okay, this was example 1 based on robots, maybe simple to understand, but not quite what we're doing in our experiments. Example 2 is a bit more related, so that would be sampling from unnormalized densities. This is a reminder of the SOC problem up here. And now I'll talk about what sampling from unnormalized densities means. So the challenge is you're given a function g, such that the integral of e to the minus g is finite. And you want to generate samples from this distribution that's pi proportional to e to the minus g. This is a problem that's very common, and it has applications in Bayesian statistics when you want to sample from a posterior. It has applications also in computational physics when you want to perform free energy computations. And the common approach is our MCMC algorithms. So what you'll do is you'll have this Markov chain, which you construct using gradients of G, and then you add some noise. And I'm sure a lot of you are familiar with MCMC. The problem is they struggle with multimodality. So say you start your MCMC, your Markov chain in this mode, then maybe you'll probably succeed to reach this other mode, but maybe it's hard if you're not using something that's really ad hoc to switch to this other mode up here. So these algorithms are very classic, but of course, they have their issues. And it's nice because there's a stochastic optimal control approach to sample from this. So the only thing you have to do is you have to set particular values for F and G. So this is the original problem. F and G are arbitrary. And if you set B to be just identity, you set T to be as large as possible. You set that function G to be the terminal cost, and the state cost you set to be minus the divergence of B, which is just a constant. Then you have that for the optimal control, you'll be able to basically simulate the control SD and take the very last iterate, and you'll be guaranteed that this is a sample from pi. Of course, the whole thing hinges on you being able to actually learn the optimal control, but that's why we're developing better and better techniques to solve SOC problems. Okay, so that was example 2, and feel free to interrupt with any questions. Otherwise, I'll go into example 3.
The thing you hear is a question.
Yeah.
There's one by Christoph and one by myself. Christoph?
So just maybe I didn't get it. So for the energy functional, the motivation to formulate it like this, is this something you came up?
No. Sorry. Yeah, this is a good point. So this is a paper by Berner, Richter, Ulrich, 2020, and also path integral sampler, if you're familiar with it. So that's a paper from 2022.
Ulrich from TU Munich or a different?
From Meta.
Okay.
And Ulrich.
And but because like looking at this from a variational perspective, this I would expect seeing not this discretized version, right? So maybe more you have a functional view on it, right? So this is a function on your state space, and you have your data term in there, but this is more you measure on the discretized samples, right? The difference somehow. Is this like the interpretation of it, or I just want to get a hand on this term, on this energy functional.
I'm thinking of this as just like any energy function that you want to care about. It gives you basically an amortized way to get samples from e to the minus g.
No, I mean the complete. I mean the complete thing, like the objective.
Oh, the whole thing.
Yeah. No, like you measure on the vector norm, right? On the Euclidean vector norm, right? So
yes,
and not like
yes,
on
exactly.
the L2 norm of the function somehow, right?
Exactly. Yeah, you're right. Yeah.
And I would like to understand like the motivation for doing this.
I see. So okay, so that's a good point. Like you could think of, okay, why not have like more general costs on you? There are reasons that well, at least these are important, and they're both, well, just the first reason would be that when you have like a control cost, that would be the control cost term of this form, there's actually this path integral theory that we're going to exploit that is nice and allows you to do things that you would not be able to do for more general control costs. Second, and very important reason you want to consider this kind of cost is that this term here, so expectation of L2 norm of U, is actually the divergence, like the KL divergence between the uncontrolled process and the controlled process. So this actually ties very well together with maximum entropy RL, or KL regularized reinforcement learning. So this, in fact, stochastic optimal control is just really like continuous time, continuous space, entropy regularized reinforcement learning. So there's a few reasons you want to consider that. Of course, like there's the more generic version of the SOC problem where you have essentially like any function applied on.
At least you would like to have convexity, right? Otherwise,
exactly, any convex, any well-behaved convex function applied on you. But yes, so far, like just even this particular case gives pretty interesting results, and then so we had this follow-up work which was diffusion fine-tuning, and we also use an SOC formulation of this form. So it seems like maybe this doesn't cover all, but like I would say every interesting case I've encountered, although maybe that's where I've been looking, has been covered by this formulation.
Thanks.
Okay, so example 3, that's important sampling for diffusions. Let's say, let's go back to the example I presented here with the 2 holes. We basically want to estimate the probability that the process satisfying, well, this base SD will go through the top hole. So basically, the probability that at x capital T or x1, our process will be in this interval. This is a very unlikely event, of course. So Monte Carlo estimation, which would basically mean you just sample a lot of trajectories and see which fraction of them actually end up here, is extremely high variance, basically because you'll almost never get anything up here. And like more generally, you may want to estimate quantities of this form. So expectation of this exponential. If you set f and g of this form, you're essentially recovering this probability, but that would be a more general formulation. And what you want to do, of course, is you want to do important sampling using a process that goes through the top hole often. So what you do is, well, sorry about this. This should be just capital T. You want to do important sampling. So you want to estimate expectation of f of x using a Monte Carlo estimate like this. So you have this controlled process. This is essentially the ratio of densities for the original distribution that we care about over processes and the new one. And this is something that you can obtain like in closed form using the Kirsanov theorem. And now, of course, like you want to use the U, the control U, that minimizes the variance of this, right? The whole point of using an importance variant, like important sampling approach, is that you want to have very low variance once you use it. So you want to minimize the variance of this. And it's nice because the control U that you have to plug in here to minimize the variance of this whole thing achieves 0 variance. And this is the solution of, well, you guessed it, the stochastic optimal control problem I've been talking about the whole time. So that's yet another view on why you want to solve stochastic optimal control problems. Every time you want to perform important sampling, you want to solve SOC problems. Okay, so now I'll switch to existing approaches for SOC. So this is a reminder of the control problem we're solving. When the dimension D is small, and that would mean like D less or equal than 3, you can solve the Hamilton-Jacobi-Bellman or HJB partial differential equation using dynamic programming. So this is actually the context in which dynamic programming was introduced by Bellman in the 50s. The whole thing, of course, is that you actually need to grid the space in order to solve the HJB equation in low dimension. So it's actually not scalable to high dimensions. When the dimension D is higher, there have been some approaches that have been developed in recent years using deep learning, but it seems that still the loss that was preferred or that was best performing, at least according to our experiments, among the existing ones was the agent method. And I'll just describe it here very briefly because it's actually not too complicated. So what you do is, say you parameterize the control with a neural network. So you say, I'm going to take U to be a neural network parameterized by theta. And then I'll simulate a batch of trajectories of the SD3, so the controlled SD with controlled U theta, so that I'll be able to get a Monte Carlo approximation of the control loss, L of U. Then I'll just compute the gradient of the approximate control objective with respect to theta. So note that what that means is we'll have to basically backpropagate through the whole trajectory, right? Because every time for every time step of the trajectory, we're actually using U to construct the following iterate. So this involves, this computation of the gradient involves, keeping the computational graph, keeping the whole trajectory in the computational graph, and then backpropagating through every single iterate. Once you have the gradient, you just update theta using a stochastic optimization algorithm like Adam, and you know the drill. This is just the usual strategy. There are some things you can observe about the edging method. I said it's the best performing algorithm among the ones that people have come up with. And what do I mean by that? So a very subtle way of examining how these methods perform is to look at the L2 error for the control U. So you may think, okay, we can just look at the control objective, but if you want a finer grain analysis on how it is doing, looking at the L control error for U is a good thing. So what we're looking at is the expectation of the norm squared of the difference between the R control and the optimal control. Of course, this is a quantity that we usually don't have access to because we usually don't know the optimal control. That's why we're solving the problem. But for certain for certain settings, we do know what U star is. And these are, for example, control L2 error plots along training for the edging method. So one thing you can see is that it's not very stable, right? It goes down and then it goes up suddenly and then back up and then down again and then up and down.
So how do I interpret the T in the index of the expectation?
Yes, so this would be that the T just goes from 0 to capital T. So you're just sampling a T randomly between, you just sample a T randomly between the start and the endpoint.
So you don't integrate?
Yeah, it's essentially the same thing, right? Because you could say, you can translate the expectation with respect to T. Since it's a uniform expectation, it's just saying, okay, integral of T. Yeah, it's just a way to shorten the notation.
Understood.
Yep.
And there was.
Sorry, there's another question.
Yeah.
for the previous slide, I was wondering, like you said, we would simulate a batch of trajectories from the SDE, like our training, basically our training data set.
Yeah, exactly.
But then doing training, like doing the optimization of theta, do we also, like for back propagating, do we also need to solve the SDE then?
So you solve the SDE to actually simulate the budget trajectories. So if you want to backpropagate, well, I mean, thanks to the automatic differentiation engines, what you have to do, like for example, if you use PyTorch, is you just you do with Torch grad, you just simulate the trajectory, and then you can just just run the backpropagation. But like when you write the code, you don't actually have to do much. You just have to simulate and then backpropagate. One thing you could do is, and that's something that we exploit in our follow-up work, is you can write down continuous time dynamics for what this backpropagation is doing, and that's the adjoint ODE. So you can simulate an ODE also to do the backpropagation, and that gives you a more accurate estimate for the gradient. But that's not what we meant, because that's not what people have been doing. People have been just simulating batches of trajectories, and then just using very simple PyTorch code where you take the gradient, and then the automatic differentiation engine does all the work.
Okay. But compared to continuous normalizing flows, like classical score matching.
Right. So that would be So that's a good point. So this approach here would be more like what people were doing with neural ODE, so before diffusion, where they were also just they would start from the training sample, they would go backwards in time to time 0, and then backpropagate, right? Because you want, like with continuous normalizing flows with neural ODEs, you would start from a sample, training sample, you would go backwards in time to time 0, and then you would try to essentially maximize the likelihood of the initial sample, because you knew it had to come from a Gaussian.
And then training becomes expensive because we have to do this for every step.
Exactly. You have to you have to keep all the function evaluations in the computational graph, so that requires some RAM.
I see.
Yeah.
Maybe
that's another downside of this approach, which is that if you were to use a lot of discretization time steps, then essentially your RAM would be you'd be using a whole lot of RAM.
Yeah. And maybe that's another question for later, because you will maybe comment on this. But like now, compared to flow matching, flow matching would be a solution to this problem. But
exactly. Yeah, you're right. Yeah. Because then it's kind of decoupled. So the trajectory simulation is one thing, which doesn't use a whole lot of RAM, because you don't need to store any computation, like any computational graph. Then when you want to actually do the learning, or actually backpropagate, you can do that posteriori, and you can do gradient accumulation much easier. There are advantages, more like technical advantages on that side too. But yeah, you're right. I think that's something for later.
Okay, great. Thank you.
So why? Of course, it's unclear why this happens, but we hypothesize that it's just because the adjoint loss is highly non-convex with respect to the control U. And this is writing again the control problem, but just focusing on the dependence on U. So you can see that the training loss or the control objective depends on U explicitly. So that would be, if you forget about the other U's, the small U's up here, this dependence is explicit and it's convex, but you also have this implicit dependency, which appears throughout the whole trajectory. And that's where the non-convexity arises. So when we saw this, we thought, well, can we design algorithms with stable training? And that's where I'll go into SOCM. I covered a bit the story about continuous normalizing flows earlier, but is it actually? So there's one thing, which is that this should be a P1. So yeah, this is what I was saying earlier, right? When you do continuous normalizing flows, you originally they were trained to maximize the log likelihood of generated samples. So what you do is you basically sample from. Okay, it's a bit hard because there are some. I think there are some typos with time, but essentially what you want to do is you want to sample initially from training samples, then you want to run the normalizing flow backwards in time so that you end up with the initial sample, and you want to maximize the log likelihood of the initial sample, which is essentially what this is doing. This is just the log likelihood of the initial sample. But formally, when you look at the dependence of this objective in V, it's what we had before. It's very, very similar because we have, on the one hand, like convex dependency. In this case, it's not norm squared of U, but rather divergence of V. But then you also have implicit dependence throughout the whole trajectory, which causes non-convexity. Now, if you go to diffusion models, the story is so much simpler because you only have that V appears here, and it just totally squares dependence, like functional dependence on V. So before I go on, let me make this distinction between functional dependence and dependence in parameter space. So of course, if you were to parameterize V as a neural network, which is what people do, then this loss will not be convex with respect to the parameters of V, just because this is a neural network and the architecture is very complicated, so there's no way it's convex. But it seems that just having functional convexity is a desirable thing in deep learning because our architecture are so flexible and so expressive that it seems that maybe that's the thing to look for. And again, this loss is convex with respect to V. So this I already hinted a bit to this picture, but we have these two tasks: generative modeling, stochastic optimal control, and then we have non-convex functional landscapes, which are covered by maximum likelihood CNFs for generative modeling, and then least squares functional landscapes, which are diffusion models, and lately flow matching, which has been pretty popular in recent months. And then we want to come up with, completing the square, and that's stochastic optimal control matching, which is ours. Okay, so what is it about? We start from the SOC problem, which is up here. And then we propose this surrogate loss function, which takes up this form. So what the minimization is with respect to two parameters, like two objects. So first U, which is the control, and then second, M, which is this reparameterization matrix, which is a new object that we introduced, and it's essentially going from two time variables to the space of matrices. There are other objects in this formula, so let me describe them. V is a fixed arbitrary control, so plugging any V here will do the job. So we will actually have an expectation that makes sense. There will be certain V's that will be preferred, so that's what we'll be taking, but I'll talk more about that later. W is a matching vector field. So yeah, we're essentially learning U to learn this vector field W. And alpha is the importance weight. So we have that alpha is, just some importance weight that we need to have later on, in later work. It turns out that you don't really need to have alpha sometimes, and it actually does better. But to have the whole theoretical guarantee, alpha should be there. I'm not giving the expressions of W and alpha here. I'll give them later on. Yeah, just let me say that they depend, of course, on the costs, F and Z, and lambda and sigma. So the noise schedules. So yeah, that's formally SOCM. And I'll get back to it. For now, let me give you some more details on it. So how do we derive this? Where is this coming from? So the optimal control admits an analytic expression as the score or the gradient of the log of a normalized density. this is similar to score-based diffusion. So that's the basis of our algorithm. And I'll give you some of the math. So I'll just make this a bit more formal later on. So once we use this idea, what we use is this mathematical result that we call the pathwise reparameterization trick. And this is a novel technique to express the gradient of a conditional expectation. This is where the matrices M will show up. Why do we have M? Why are we even optimizing this matrix M? So to understand that, it's nice to re-express our loss as a sum of two terms. So the first term would be really the L2 error of U. This is something that you've already seen, although in this case it's expressed in terms of this arbitrary process XV. But yeah, this is essentially how far U is from the optimal control U star. And then the other term is just the conditional variance of W. So yeah, you just have the vector field W, and then it's conditional expectation. So this normalization is such that, well, this is actually an expectation, so that the weights are actually summing to 1. Another way to rewrite this second term would be just as the optimal control U star. So you could also say, okay, so my two terms are difference between U and U star, and expectation of difference between U and U star, and expectation of difference between W and U star. So what we're doing when we train M is actually minimizing the conditional variance of the matching vector field. And this goes back to what I said earlier on, which is like good performance stems from good functional landscape plus low gradient variance. So when we're optimizing M like this, we're actually reducing the gradient variance because this term could be a source of variance. So the smaller this term, the lower the variance of our gradient with respect to the neural network parameters of U. Another question that you may have is, okay, how do you choose this arbitrary vector field V? Again, when you have an importance weight, what you want to do is you want to set it such that it has low variance. And it turns out that if we were at the optimal control, so if we were to set V equals U star, then the gradients of alpha would be 0. But then, I mean, we don't have access to U star because that's what we want to find. So in general, what we do is we take V to be the current learned control U. And that seems to work well enough in some cases. Okay, so those are, I feel like, enough details for now. I'll go back with some more later on, but I'll show you some experimental results first. So there are some. So in this paper, we considered mostly, simple experiments. We have this follow-up, which will be more like really like more of an empirical paper. But this was just at the theoretical level, just understanding what are the options and the challenges of this method. So there are 3 settings that I'll be showing here. First is quadratic Armstrong-Rielenbeck or linear quadratic regulator. I feel like this is much more common name. So you have a linear base drift, quadratic state cost, quadratic terminal cost. Then linear OU, which is the same thing. It's just that the terminal cost is linear instead of quadratic. And then this double well example is pretty different. So it's a case where the terminal cost is actually it's minus the log density of a high-dimensional double well. So it's an example where you naturally have a multimodality. So you have your system, like the SDE solution, may end up in a lot of modes. So it's 2 to the D, and we're taking D equals 10. So essentially, it's a system where our iterates can end up in more than 1,000 different places in the state space. So it's actually harder to learn the vector field. And then these are the baselines that I'll be considering. I've only talked about the edging method because it's actually the best performing among all of them. But there's a lot of, several recent works that have actually tried to propose alternatives to the edging method. And there are 2 oblations that I'll show, which is what happens when you take constant reparameterization matrix, and SOCM adjoint, which is this, I won't go into that, but these are 2 oblations of our method. And in this first plot, the variable that I'll show is the control L2R. So here's how, here's actually, I would rather just have expectation with respect to the optimal control. But yeah, this is the control L2R. This is what I told you about before, and these are the results. So SOCM is like an order of magnitude below any of the other methods, and actually the second best ones are also our ablations. The adjoint method is here in purple, so you can see it up here. This is a bit somewhat of a more challenging setup, but SOCM is also the best performing one. And here SOCM, this is again linear OU. SOCM also does better than the other ones. And then one of our ablations actually matches SOCM. And in double well, this is where adjoint was showing this instability. It's hard to say that we do better than adjoint, but adjoint is not stable. So yeah, that's basically the result. And then I told you about this importance sampling perspective on stochastic optimal control. So what happens when we look at the importance sampling weight of like the variance of the importance sampling weight? Of course, yeah, we know that if we were at the optimal control, that variance would be 0. So that's also some kind of metric that we can track to see how well we're doing. It's a bit less precise in that it allows us to, like, it doesn't allow us to distinguish the methods as well. But SOCM also does better. And here, weirdly, adjoint does best. But when you look at double well, SOCM does best. Okay, so these are some metrics. And like going back to having a bit more understanding on our method, remember that our loss was the sum of the L2R of U plus the conditional variance of the matching vector field W. So what these plots are showing are basically the training losses for SOCM. So that's our algorithm where we're actually training M. Then the SOCM ablation, where we set M to be constant. And SOCM adjoint, which is another ablation of ours. And here we see very clearly that when we optimize M, the training loss is actually going to 0, which means that both the L2R of U and the conditional variance of W are going to 0. While for the ablations, well, the L2R of U is actually pretty close to 0 because that's what we saw in the previous slide. But when we look at the conditional variance of W, it's not so. And of course, that means that our gradient is more noisy. Same story for all of them. Actually, in one of them, like here, SOCM adjoint actually manages to get very low conditional variance. But this is a story that seems to be consistent. Okay, and then I don't know if you have some questions on this. Otherwise, I'll go into maybe briefly into how you derive the SOCM loss. So these are reminders. XU is the process controlled by U, and it's the solution of this SD. While X is the uncontrolled process, so it's a solution of this SD. And this is the path integral representation of the optimal control that we use to derive our loss. So what this is saying is it's actually a nice expression in that it gives a pretty explicit dependency between the optimal control and the costs of the problem. So that's the state cost F and the terminal cost G. So it's telling us if we want to find the optimal control, we just need to take sigma transpose times the gradient of the log of the expectation of this exponential. So what are we going to do? We start from like this theoretical loss that of course we cannot implement because it involves the optimal control, but we can rewrite it. So what we do is we start from this and we expand this norm squared of the difference into 3 terms. Now, once we're here, we're going to take this cross term and we're going to write it using the path interval representation. So when going from here to here, we basically use this, but we write the gradient of the log as a gradient of just the expectation over the expectation. And note that we can cancel out the gradient, like the expectation, with what was up here in the numerator. So we only have this thing left in the numerator. So there's a simplification that went on here. And then now that we're here, we essentially want to evaluate this, or we want to have some way to estimate this, some unbiased estimator of this quantity. And this is where the pathwise reparameterization trick will appear. So we want to compute the gradient of this, and our proposition, which is new, tells us that if we want to do that, we can take an arbitrary continuously differentiable matrix valid function such that m at t is t at t is the identity, and then we have this. So this is a bit, this is not a straightforward expression, but the whole point is that looking at the right-hand side, we can actually estimate this via Monte Carlo estimation. So what we're going to do is we're going to replace this factor here by this thing, and we complete the square. So that thing appeared here. So we're just going to replace this by what the pathwise reparameterization trick tells us, and eventually we end up with this loss. Now, this is not quite the SOCM loss, but it's almost it. And the only thing we need to do to get it is to perform a change of process from the uncontrolled process to an arbitrarily controlled process xv, applying the Gersonov theorem. But that's just if you're familiar with the Gersonov theorem, that's really just one line. And then we obtain the SOCM loss. So here, just so that you have the whole expression once, I'm showing the expressions for the matching vector field and the importance sampling width. So that's how you derive the loss. Now I'll go into future directions within of this line of work.
There was
sorry.
I have a quick question.
Yeah.
About the last step where the v xv comes in.
Yes.
So very naively, why do you have to add the v then?
Sure. So that's again such that you have low variance. So if you say you consider this loss, and you didn't want to make the change to an arbitrary phase process, so what would happen then is that most likely this factor here would have high variance. So when you go from x to xv, this factor here becomes the factor alpha. And note that you have basically the same terms here, but you have these other terms. And this whole factor actually has lower variance than if you just had this. And in particular, if you're at the optimal control, alpha has 0 variance. So you really need to make this last change in order to go to, the most favorable vector field that you can use to lower the variance weight, the variance of the importance sampling weight as much as possible. And this is a good question because, I mean, I have not discussed this, but I feel like just for whole transparency, it's worth doing it. So that the issues with this loss is actually the importance, the variance of the importance sampling weight, right? Because anytime you have an importance sampling weight that is an exponential of something, if this has just a bit of variance, then the exponential of this will have a lot more variance. And if that happens, then the algorithm fails just because the signal to noise ratio is bad. So yes, so this is an algorithm that works very well in some cases, which is why I think it's interesting to consider. And as an approach, this idea of framing losses as least squares losses I think is good, and that proved to be true because we now have like a good practical algorithms for diffusion fine tuning in very high dimensions that are actually the best diffusion fine tuning algorithms. So some things were good about this project, but there are some downsides that are hard to overcome. And the main one is, I would say the main and the only one is just this exploding variance for this, not only this weight, but clearly this one, but even just alpha can have issues when F and G are large.
Yeah, okay. Maybe another naive question, like why do you call this an importance weight, like the whole factor, or like in this case then the alpha?
Yes, so that's a very good point. It's an importance weight because ideally, so what you're trying to do by adding this factor is you're trying to pretend that you're sampling from the optimally controlled process. So that's what alpha is doing essentially. If you were sampling from the optimally controlled process, this would be a constant, which means that you would not have any important weight, which means that what you're actually doing is important sampling to be able to sample from the optimally controlled process. It's an important sampling weight.
Yeah. So during training, alpha kind of controls or like puts a weight on how off we are from the actual.
Exactly. And so let me tell you also, and this is something that I also put up soon on a separate work, which is that you can remove alpha, and sometimes like for a lot of settings, you actually get good performance. You don't get very good theoretical guarantees, but you actually converge, and you converge to the right thing. So I know that because I basically rerun these experiments with alpha set to constant, and it actually even performed slightly better than SOCM. So we call that unweighted SOCM, and it actually works. But sometimes it doesn't, because it just has no theoretical guarantees, and sometimes it actually doesn't converge. I think that's okay. And I feel like this is not really that worth going into because this is something I wrote like some months ago, but then the way our research evolved is we went into diffusion fine tuning, and it was still SOC based, but we didn't. Yeah, we took some ideas from SOCM, but eventually what we end up doing is a bit different. So yeah, this will come out in about 2 weeks or so.
Okay, great. Thank you.
Yep. So sorry, I think that's it. You can, so if you want to see derivation of the pathwise reparameterization trick, I added 2 slides at the end, just to sketch how you derive that. But I feel like there's no time for that, and I can share slides if you want.
Nice. Thanks a lot, Carlos.
Yeah, thank you for listening. I think that was a great audience.
It was very interesting. Ricky mentioned some details before. I met him at ICLR.
Oh, nice.
But I find your work very interesting.